Hi everyone again. So today we're going to talk about chapter 18, rotation in two dimensions. I am skipping quite a few chapters that is going to be about relativity because I myself haven't understood it thoroughly, so I will put it in the later chapters. I tried my best to take away all of those reflections from the lines. But there are still some remaining over here. So I will try to write all of my writings below this line so that you can see it more clearly. So in today's lecture, I will talk about the center of mass, why we need the center of mass. Then I will talk about rotation of a rigid body, how rotation is done on a rigid body, and what we need to know to describe that rotation. After that, we will learn about angular momentum, which is a very important thing to know about. And at last, you will be introduced to the conservation of angular momentum, which is one of the most important concepts in physics. So first, about the center of mass. So as we know, in the previous chapters, we've talked about the motions and the kinematics of a particle. But the particle is kind of easy because there's only one thing that is moving around. It's not really that complicated. And then, so for the next few chapters, we will talk about a more difficult thing, which is the application of Newton's law to rotation. So there are actually other more complicated and more difficult things, such as water, how water flows, the laws that govern pressure, and all other things. But first we'll talk about rotation. So, but although these things are all very complicated, but you will find out that it is nothing but F equals Fa. Because these, rotation and other things, they are just an extension of this F equals Fa. It's all governed. The ground is Newton's laws. So first, introducing to you to plane rotation. So first you will need to know about a rigid body. So a rigid body, I will tell you more detailed when we go down. But first, we will say that a solid object that is turning as it moves about. So for example, if I have a axis over here, and then I have a string connected with a block and then this block is turning. So what you will find out in this thing is that we have a fixed axis and we have a rotation of something. So this is because I am drawing this on a board, and you can see that this is like a bird's eye view of this rotation. So this is a two-dimensional one, and this is a plane rotation. So such rotation of body about a fixed point, about a fixed axis, is called a plane rotation, or rotation in two dimensions. So next we will talk about the center of mass. So introduction. So first, I will give you a phenomenon, and then from that phenomenon, I will introduce you to why we need center of mass and why is center of mass so essential in physics. So first, just imagine if you have a bunch of objects that is connected by a string. So you have like a block, you have a spoke, whatever thing, and then they're all connected. And then if you throw this thing, this something, then in the air, in a certain direction, let's just say like about 30 degrees, then you will find out that this obscure thing, it will wobble, it will jiggle, it will rotate, and it seems very complicated, isn't it? But there is one thing that is kind of obvious. You will see that this thing will move in a parabola, just like how we throw a tennis ball. Yeah, I think this is a tennis ball. So it's if you know if you have observed that if you throw this, it will be in a parabola, then it seems that there is a point in this obscure collection of things that is going to be on this parabola, that is going to be like a thing that we are going to mark it down on a grid that you will draw, and then you will connect all of those points, and then you will get a parabola. So that point is what we call the center of mass. And a center of mass, it can be on a subject, it can be on an object, or it can not be on an object. For example, on a tennis ball, then the center of mass might be in the center of the tennis ball. But in this obscure collection of things, then it kind of will be not on either of these objects. It might be somewhere here, it might be somewhere here, and who knows. So first, so now let's prove how we get the expression, the derivation of center of mass. So let's say that we have a particle that which is indexed I. So we have a particle that is indexed I, and then so what is the force that is acting on this little particle, little object? We say that there might be a force. It's only might, so we don't know whether there is a force or whether there is not. But this doesn't prevent us from writing down the equations of this. So we have that this is a force, and remember it's a vector of this little indexed particle I. It shall equal to the mass of this I times the second derivative of the distance that it shall move or it shall not move, and who knows. This is going to be the second derivative over here, and then by time. So this is like a derivative by time. And we know because that mi will be a constant, and in rotation we will deal with objects that is moving much slower than light. So it'll be non-relativistic. So it will, although it will still obey the relativity laws, but we can see that, but because the speed is so low, then we can assume that we don't need to consider Einstein's laws. So, because mi won't be changed, so we can put it into this bracket, so which will give us, this will be times, because this is also times, so just put it back in here. And then divided by the second derivative of time. So this will give us this thing. And then, because this is the force on a particle indexed I, then how about that we have an object, a system, a collection of many objects, of many particles that has the index of I. So I can be 1, 2, 3, 4, 5, and then all the way up to 10 to the power of 23. So what is the total force on this entire system? So how we can interpret it is that, let's say that we have a object over here and it has like a whole lot of particles inside, and then these particles are indexed by I, and the I is going to be increased from 1 to a huge number, who knows. And there is like a force acting on this particle, direction, in all like directions we can think of, or it might not. So what is going to be the total force? So the total force will be sigma, which we know that this is the adding notation. So it will be sigma of I, and then you times it by, I mean, you don't times it, it is like the sum of all of those independent little particles, and then it shall equal to the total force. This is the total, and this shall equal to the second derivative of Ri times, well, we have to put a sigma over here because this is like you're adding together them all together. So it'll be Ri times Mi, and then divided by t squared, dt squared. So all of this thing. And let's move on. So now I will introduce you to a new concept, which is that the total force on the particles inside this little system, it will be equal to the external forces. So what I mean is that going back to this example, in this little area, that's going to be the particles that are interacting with each other because of Newton's third law. Like there is action equal to reaction, and then all those action and reaction will be on one line, opposite directions. So this will be one system, and then the internal forces will be all the particles acting together with each other, and then the external force will be a force that you're going to push this little object. So we now know that the total force on the particles is the same as the external force. So if we add up all of these little forces on each particle, it shall equal to the total force. The total force shall equal to the external force. So why is this correct? So this is because of Newton's third law. Action equals to reaction. So because this is in two dimensions, so let's say that let's take out a particle and also another particle, and then let's draw a coordinate system. So we now know that this object, this particle, there is a force in this direction, and there is also, and then for this particle, there is a force in this direction. And then if we take the components of these forces, then it shall be over here, and over here, we can decompose them towards the x and the y directions. And because this is what we call the origin, so the forces in the x direction and the forces in the y directions, they will cancel out. So forces which arise from other particles which are not included in whatever object we decide is the sum over, because they are cancelled out. So the thing that is left behind will be the external forces. Yeah, this does make sense. And this is an example of how I explain this. So now we have this thing right over here, and then wait a second. Let's say that we define manually, artificially, that there is a vector r, and that vector shall equal to the sum of all i's of mi times ri. And remember that ri will be a vector divided by m. So m is like the total mass. So this is a vector that we have to mathematically define. And then now let us look at what the relationships there are with this r and over here. So you'll notice that there is kind of something that is the same, which is over here and over here. So we can rewrite this total force as a subject, and then we will have r inside it. So now let's say that our total, it shall equal to dm, and then mr divided by dt squared. So as you know, we timed a big R over here, a big M over here, and big M will be the total mass. And then this, if it's times over here, then it will be cancelled out with here. So it shall remain the same thing. And we know that big M, which is the total mass, is a constant. Thus we find that the external force is the total mass times the acceleration of an imaginary point whose location is R. What it means is that we can take this M out, which we shall get M times dr over dt squared. So now we know that the total force, which is the external force, is equal to the total mass times the average point, which we call the center of mass, which is a certain location in the system, and this shall equal to the internal forces, and it shall also equal to the external force. The sum of the internal force, sorry. So now, we call this R thing, we call that this will be the center of mass. So now we have a remarkable new concept, which is the center of mass, and then I will only introduce you to some of those limited knowledge about this, because there will be a more concise and detailed explanation of center of mass in the later chapter, which I am working on right now. So, the first point is that if external force are zero, then the center of mass will either be moving at constant or it shall be still. So what it means is that, let's, for example, we have a spaceship over here, and then there are some people who are sitting inside the spaceship, and then we know that the center of mass shall be somewhere over here. So let's call it, this is going to be our center of mass. So this center of mass, it shall be constant, or it shall be still. It shall be moving at a constant speed, or it shall be staying at still. So this is something like Newton's third law. Like if there is a force acting on this center of mass, then it shall be accelerated. But if the external force is zero, then it shall be at still, or it shall be moving at a constant velocity. But it is not the only kinematic that it can do to move around like this. There is also another way of moving that it can do. It can wobble, it can jiggle, and it can twist, which means that it can rotate itself. And if it rotates itself, and then we say that there is an axis at the center of mass, then we know the center of mass will not be changed. And so there is an analog. So for example, that there are people who are sitting inside the spaceship, and then there are some crews. So this will still be the center of mass, but if one of those people, they want to go to the back, then because their mass has changed the center of mass, because as you can see from over here, the center of mass is actually somehow the average of all masses relative to the distance of them from a fixed point. So the center of mass, if he comes here, then the center of mass might move here. I don't know if I have done it in the right direction, but in the right direction. But anyway, so it might move over here. So, but still, the spaceship, it has to stay in this position relative to a frame. So what it has to do is that it has to move in this direction to stay in that direction to maintain that the center of mass will be changed. And secondly, concerning the sense of mass, so why do we need the sensor of mass? Why is sensor of mass so important? So because I have introduced you to this concept that the sum of the total force in the system is equal to the external force. So what we know right now is that we don't need to calculate all of those millions and billions of particles in the system. What we all need is only to calculate the outside, the external force, which makes our calculation more simple, less complicated, and the number of things that we will deal will be reduced from 10 to the power of 23 assumed back to limited forces, or it might not be limited. So it may be treated separately from the internal motions of any object and may therefore be ignored in our discussion of motion. Our second part will be the rotation of a rigid body. So if something rotates, for example, I rotate my arm, so it does not only rotate, but you will feel that there is like a stretchy force when you try to rotate your arm. So if we zoom in into the tiny world, then you'll find out that there are tissues that are stretched. So rotation, it is not only rotation, but there is also other changes like the shape, the size, and then all other things. But if you want to study rotation as a student who hasn't studied rotation before, then all of these things will be too much complicated, and it's out of our reach. So what we will now do to solve this problem is that we invent an ideal model called a rigid body. So a rigid body, it is a body that the intermolecular forces are so strong that no matter how fast we rotate it, the particles will still be sticked together. So this is how you spell rigid body. Yeah, rigid body. Okay. So they will be still. So why we will need a rigid body? First, it will simplify our calculations so that we don't need to consider all of those other factors. And secondly, it's much more easier for us who haven't learned something to learn about it. So the study of a rigid body. So if we agree to ignore the motion of the sense of mass, what I mean is that, for example, we have a cardboard over here, and then we agree that at this sense of mass, there will be no forces actually on it. So this sense of mass, it will not move from here to here. So it will not move from here to here. So if it can't move from here to here, the other thing that it can do is that it can rotate. So if this cardboard, it can rotate. So because we're studying physics, and so we need to describe it. For example, before in the previous chapters, we have a particle that is moving from here to here. Then we are introduced to by Feynman a whole lot of kinematic models and laws that are all governed by Feynman. So if something, this cardboard, if it is also rotating, then you still need to describe it. And then if we can describe it, then we can do experiments, mathematical derivations, so that we can find other theories, other deductions that we can get from this description. And if we push this thing to engineering, because we have an entire system of describing a rotation, hence we can predict something of happening, so it helps us a lot if we know how to describe something. So first, suppose that there is some line in the body that stays put when we are rotating it, and that line will be on the axis. So what I mean is that, for example, we have a plane over here because we are studying plane rotation, which is two-dimensional rotation. And then this will be the center of our rotation, which will be our center of rotation. And then there will be an axis. So an axis is an imaginary line that is penetrating through this, and it will be perpendicular to this plane. So because of this board is only two-dimensional, and then if you want to imagine it, it shall be in 3 dimensions. But there is, so just imagine that this pen, this marker, it is a line, and then we stick it down in here. So this will be our axis of rotation. And how do you define the rotation? Let's say that you have a particle over here, and that this particle is rotating about this axis, and it rotates from here to over here. So this is how it rotates. So because we know that in the studies of a particle which is not rotating, we will want to know the position of a change, right? But this is a different scenario. This thing is rotating about this axis. So what we all need to know is the angle of rotation. We'll need the angle of rotation and also accompanying with the positions to help us, to guide us through. Rotation consists of a body of variations of the with angles, with a change of angles. What this means is that rotation, it is a movement of something that has to do with the change in the angle about a fixed point. So now we will have a closer look at how to describe rotation. So first, the kinematics of rotation. The way that how Feynman introduced rotation to us is with the analogy of linear motion. And that's how I will also lecture, how I will teach in this lecture. So let's say that angle theta defines how far our body has went around. So now we have a coordinate system. Now we have this graph, this axis, with a point P which has the coordinates of x and y, and this particle at this point P, it rotated about this original axis to Q, which is at this point. And now let's determine how we're going to describe this. So if we want to describe this, so first we will try to describe how the x and y changed. So first, how the x changed. So as you can see that there is a change in x, and then this x will be this long. Although this is the velocity of this particle rotating, but the length of how the x changed will be the same as the x component of the velocity. Because as we have studied in geometry, this line will be perpendicular, and then we know that the velocity of this particle moving, it will be tangent to this arm, to this line. So this is also a right angle, and thus this is also a right angle. And because of geometry, we know that this angle is equal to 90 degrees, and this angle will also equal to 90 degrees, and this angle at this theta will also give us 90 degrees. So there will be a equal of this angle V, P, Vy, and it shall equal to this theta. Yeah. So because now we know that this angle is theta, so it will be easy for us to calculate the length of this thing. So PQX. So PQ, the first we will need to know this length. So this length will be how far this particle has traveled. So PQ, it shall equal to R times delta theta. And something to note about is that this delta theta, it is in radians. So because that this is a rotation, and we know that in a rotation there is like somehow an arc, and in this arc there is a change in angle, right? And so in mathematics class we know that the length of this arc will be delta theta times r, and this delta theta is in radians. But the reason why we also call this length delta theta times r, is because that we assume that this delta theta is very, very small. So if it's very small, then we can assume that the displacement is a straight line, just like how this is done. So it shall be ignored. So now the change in delta x, it will equal to the negative of PQ, because we defined that if we go from this direction it will be positive, and if you go from this direction it shall be negative. So it will be negative PQ times sine theta, which is over here. And then now, because this theta equals to this theta, and then we know that we're taking the sine of this. So sine theta is equal to y over r. And if we substitute the sine theta into this delta x, then now we know that delta x is negative pq times r over y. And if we substitute pq also into this delta x, it will give us delta theta times r and y. And this r will be cancelled out, so it will at last give us delta theta times r. And if we do this same manner with the change in the y direction, then we shall also get the change in y direction. So I will not write this change in y direction, so I'll just write it down. So for the reason why delta y is equal to plus delta theta times x, it is equal, it is the same reason. This is, so it will be the same derivation. So now we know how it changes. And because that this is a rotation, and as I have said before, that rotation, and we have to describe it with the change of an angle. So now we define, you will be introduced, well, we can't really say define, because in the 12th chapter, characteristics of forces, Feynman said that it is useless to define things. It is important to know what it is, but we can't define something. So now we introduce a thing called omega, and omega will be the angular velocity. So angular velocity, what is angular velocity? Angular velocity is how fast an angle is changing. How fast an angle is changing. And the angle, how fast an angle is changing, and because that in this scenario that we have derived delta x and delta y, we have pinpointed these 2 points P and Q. But if this particle that is originally at P is still moving, then it has the velocity of changing on its angles. So now we will substitute this omega, which is the change in angles, which is the same in these both things, to delta theta. So the Vx and Vy, it will be equal to, the Vx it will be negative omega times y, and for Vy it will be the plus of omega times x. And if you want the total velocity, which as you can see from this diagram, we have calculated Vx, which is the velocity in the x direction, and also Vy, which is in the direction of the y direction. if you want to calculate the total of V, then the quantity, the magnitude will be equal to Vx squared plus Vy squared. We'll take the velocity, and it will be equal to omega squared y squared plus omega squared x squared, the square root of this thing. And then because that omega is like the same term for x and y, so we can take omega out, and due to the square of omega, so we can take it out of the square root. So it will be omega times the square root of y squared plus x squared. And due to Pythagoras' theorem, y squared plus x squared is equal to r squared. So this expression will equal to omega times our r. Well, this is correct. Well, obviously this is correct, but there is also another way that we can come to this solution. So the velocity is velocity is magnitude. We know that velocity is the travel in the distance divided by the time. If a particle originally at P, it traveled to Q, so the distance that of a travel will be theta times r. Times r, this is delta r. And because if we divide it by time, delta t time, then we shall get omega times r. Because we have defined that omega will be the change in the change in angles. The speed of how much the angle changes. After introducing to you these basics, now we shall move on to another thing, which is the torque. Do you remember that before I derived all of this, I said that we are going to explain rotation in analog to linear motion. So this omega thing is the speed of how much the angle, the speed of the change in angle. It's not the change in angle, but the speed of this motion, how much this angle. Yeah, you know what I mean. Yeah. So this is like the velocity. This is like the velocity in our linear motion. And then if we divide it by delta theta, by delta t, then it will give us the velocity. So now a new concept must be introduced, which is the force. This is in linear motion. If a particle needs to move from still to move, then there must be a force due to Newton's second law. But that is in linear motion. Now, if we come to our rotation, then there shall be a rotary force that is going to make a particle at P move to Q. So this rotary force, or this twisting force that we are going to talk about, its scientific name is torque. So torque is what causes something to rotate, just like force causes something to move linearly. So how will I explain torque to you? Feynman taught me to explain torque in a quantitative way, which revolves about the work. So it is a very nice way to find for you to say how much work it does when it acts on something, on a given displacement. So we will talk through an analog with linear motion. So now consider a rigid body, which we can use this original one, I think so. So if we consider a rigid body and we concentrate on only one force of that body, which is going to be the force on Q, the force on P on this particle originally over here. The reason why we will only concentrate on one force is because that if it comes to two forces, then it will be too complicated to introduce you to a new thing. So the change in work from a particle rotating from P to Q will be equal to the distance, the change in distance times the force, which is what we have learned in linear motion. So because that it is not in a completely straight line which is perpendicular to the y-axis or the x-axis, so we will calculate the change in work by the change in x direction and also the change in y direction. So the change of work will be equal to f x times delta x plus f y times delta y. And because delta y and delta x equal to this part that we have derived before, so now what we will need to do is just to substitute it into here. So now it will be delta w, which will equal to negative delta theta y plus fy times delta. So delta y is equal to delta theta times x. And because delta theta is something that is common in both terms, so we will take delta theta out. So now we know that change in work will be equal to delta theta times x times fy minus y times fx. So now you can see that this strange combination over here. So this is what we call a torque. So what's analog to linear motion? In linear motion, we know that the change in work is equal to the change in displacement times our force, isn't it? So now, delta theta, it writes how much something turns around. And over here, delta d writes how much a particle has moved. So it's somehow, it has the same meaning inside it. And then, because we know that this W times the force in the direction of the motion, and then this will be delta theta times this whole entire thing, which we will call this thing torque. So torque is, because that over here in this strange combination, we found out that there is Fy and also Fx in this. It is not completely strange to be introduced to a new idea that is independent of Newton's law, because what we are trying to describe is a motion, and a motion of what we are learning right now is governed by Newton's law. So it will have to be an F inside. However, this is only a force acting on only one force acting on one particle. But if we have many forces acting on one particle, so how will it be then? So now I will erase this and I'll put the important things on top. So delta theta is equal to delta W is equal to delta theta times x Fy minus y times Fx. And I will erase this. Now we will consider a particle and it has different forces acting on it and then it's still rotating. So how will the torque be? So because that we know that we are going to derive the torque from the change in work. So the delta W for total, which I will denote as delta WT, it will be the whole of all the terms of this thing times delta theta. So now you will know that if you want to calculate the total work done, it will be something that is proportional to delta theta times delta theta. And that thing that is proportional to delta theta is this thing. I mean, the work is proportional to delta theta, so and then HL times this, and that will give us to the total delta W. We can take the delta theta outside, and therefore we can say that the change in work is equal to the sum of all the torque due to all the different forces that is acting on the delta theta. So what it means is that we take this delta theta out over here, and this delta theta is going to be like constant if we times it over here, because what we are describing is a particle. It has like an origin over here, which will be the axis of rotation, and this particle, it has like different forces acting on it, but the same thing is that it rotates at its delta theta, so we can take this delta theta outside. And because we want to tell the total, so the total will be delta theta times this whole combination of things added together. And the sum is the total torque, so the sum of this will be the total torque. And now, how will we denote total torque? The total torque will be tau, which is, I think it's like pronounced tau, I'm not really sure what it is. So if the torque on a particle, it will equal to xi times fyi minus yi times fxi. Okay, so this is the torque on one particle of one force. But if we want to tell the total torque, then it is not really that difficult. We just need to sum the torque up. This is how we'll get it. So the torque adds by as you can see, we added up all the torques. So what is the conclusion? The conclusion is that torque, it adds by the ordinary laws of addition, of ordinary algebra. This is kind of the same as how we have talked about force. So in forces, we can add a force together. So for example, if we have a box over here, and there are two forces that are pushing this box. One is 2 Newton and the other is 1 Newton. So the total force will be 3 Newton. So we just simply added this 1 Newton and then this 2 Newton thing. And but also, it must be emphasized that when we are talking about the torques and the chains of blah 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 blah, we have to emphasize that it is turning about an axis. It is turning about a certain axis. Because we are now currently learning about in 2D, but if we escalate it to 3D, then there are like 3 axes that we need to consider. But over here, right now, we're only considering about 1 axis. So, yeah, we have to emphasize that it is kind of important to mention which axis it is rotating about. Now, these are all kind of geometry and algebra. So now we will talk about the geometrical essentials of a torque and how torque will amount to if we do the calculations geometrically. Now let's see that what we can get that is different where if we calculate all of these concepts in a geometrical way. So we'll find out that there will be 3 ways to calculate this tau, which is the torque. So the first way that we can calculate it is the work done is the component of the force in the direction of the displacement times the displacement. So if we have, if we just imagine that there is a particle over here and then it is not rotating, but it somehow went from here to over here, and then there is a force that is acting on it over here. So because that we know the work done is equal to the displacement times the force acting in the displacement. So the force that counts is only the force that acts in the motion of that particle. So the force that is not in the direction of the motion, then that we don't need to consider about that. In other words, it is only the tangential components of this force that counts when we multiply it by delta theta, and we will get this delta W. I mean, this type of delta W. This is actually kind of easy to understand. Just imagine that if we have like a stick over here, or if we have a string over here, and then if we pull this string with a force, no matter how hard, in the direction of the string, which is in a line of the string, then this thing will not rotate, will it? And this is the same with over here, because the force is in this direction, so we can decompose it. If we decompose it, then we will find that the only force that is needed is the Ft. And if we are now, the second thing that we can know about is that a given force is more effective on the long arm than near the axis. So the reason why it is this, we can think that if there is a force that is acting directly on the center, or on the axis of rotation, then there will be no rotation. Instead, it will be moving linearly, but that's not what we want. So this is like you're pushing this arm, we're making it shorter, and then we find out that it is less effective. So the amount of torque is also proportional to the radial distance times the tangential component of the force. So that is our second new way of calculating it. Well, I think when you go down, we will know the specific formula to calculate it, but now I will only introduce you to the ideas of it. So the third way that how we can calculate this torque will be the lever arm times our force. So as you can see, that the lever arm is shorter than this arm, and as before, we know that it shall be the force, the tangential force times this arm, times this radial distance. And because that if we say that this angle will be alpha due to geometry, there are three right angles over here. So this alpha plus this shall be 90 degrees, and this plus this will also equal to 90 degrees. So this angle over here, this angle will be alpha. So if we take the sine of this alpha times by r, then we will get this length. And this length will be our lever arm. So it will be our lever arm times this r, this radial distance times sine, and then times the entire force. So this is our third way of calculating our torque. The last thing that I will talk about in this, the second part of our lecture, is an object's equilibrium. So if an object is at equilibrium, there is actually two criteria. The first criteria is that the total external force will equal to 0. And the second thing is that the torque is equal to 0, which means that there will be no rotation. So there is actually two criteria of something to be at equilibrium. So if there is only the first this thing is not moving, but it is rotating, then you can't say that this thing is at equilibrium. So if you want to say that it is at equilibrium, you need to add that this thing is not rotating. If it is not rotating, then we know that the delta theta will equal to 0. So the work done will be equal to delta theta times the torque will also be equal to 0. Yeah, and then the torque, we know that the torque is the lever arm times the force, and because there is no force, then the torque will also equal to 0. The third part of this lecture will be angular momentum. From the name, you will know that we will talk about momentum, and then this momentum will be different from the momentum that we have learned before, because there is an angular that is going to describe this momentum thing. So you'll know that it will be something to do with rotation. So there is a remarkable theory which states that the external torque is the rate of change of the quantity L. And this L is what we call momentum, angular momentum of a group of particles. So what it means is that in linear motion, we know that force is the change in momentum P. So will it also be the same in rotation? And the answer will be yes. There is also torque will be the change in L, which is angular momentum. It is like analogically related with force, because in linear motion, if you want something to move, then you have to apply force. And in rotations, if you want something to rotate, then you have to apply a torque to that thing. So if you take the time derivative of the both of them, then you will get something new, which is momentum and angular momentum. So now let's try to prove. This thing. Like it really exists mathematically. So first, let's say that we have a particle over here, and this is the axis of rotation. And then this particle over here, it rotated from here to here. And as we know, this will, in real time, in reality, is an arc. But we will not take it as an arc. We will just take it as a straight line, because this delta theta that it moves through will be very, very small. And this will be theta, and it is also important to tell you that there is a perpendicular line over here. So first, what we need to consider is there's only one force that is acting on this thing. The reason why we consider one force is just to simplify our calculations. So we know that the torque is equal to this formula. So now we will have that a torque which will equal to x times the Fy minus the y times the x. So this is the force. And then what we want to prove is that the time derivative of something will give us this torque formula. So really, does it exist? And the answer is yes, because we can mathematically rearrange this thing into this formula, into x times m over dy squared over dt squared divided by, and then minus ym, and this is dx, this is dt. So I will not really show how the mathematical way to derive this thing, but the only thing that we can see, is that if we change it into over here, what we did is that we substituted this Fy into, we expanded this Fy and Fx into its original form, into the other form of it. And then there is this formula that I will write it down over here. So if you're interested in it, so here is the full derivation, but I will only briefly tell you how it is done. So because we want to find we want to prove that this is a derivative of something equals to this thing. So it does not really mean equals to that. So it must be a derivative. So what we want to know is that this tau is the change in something. And then if we expand it, we know that this is the second derivative. And this is also the second derivative. So if you take the second derivative of this thing out, then we will have this bracket thing. And then we add dx dt and dy dt. If you add it, so you should subtract it. So you subtract it over here. Okay, I think like that I added the camera. So if you subtract it, you subtract it over here. And then at last, it turns back to this equation. So that we find out that it is actually a derivative of this. So if you take the derivative of this formula, then you will find that the derivative of this is actually equal to this tau. Yeah, so the derivative of this is equal to this, and this is equal to tau. So it is true that torque is the change in something, and then you call that this change in something angular momentum L. So you call it this is equal to angular momentum L. So L is angular momentum. And it is also quite important to note that this is relativistically correct, which means that in Einstein's world, this thing is also correct. And if we investigate, if we look at this more carefully, what is this? M times dy dt. Isn't it P? Isn't it momentum of linear motion? So this is so now we can see that physics is intimately connected. So we can rewrite this. So we can rewrite this L. We'll rewrite this L as x py minus y px. So this is one way to calculate it. But just like torque, we have three ways to calculate torque. So it is also the same that we have three ways to calculate this angular momentum. So this is the first way of how we calculate the angular momentum. The second way is R times P, that is tangential to the motion. So for example, in this graph, we have a velocity that is making the particle rotate, and we know from before that the torque can be calculated as the R times the tangential one. So it will also be the same for R times P tangential. So we can interpret it as during the torque, and it is the antiderivative. Blah blah blah. Just forget it. I think that's a mistake that I wrote here on the mind map. So from this equation, we can see that the further out this R, this radial distance, then the larger the angular momentum. So that is the first way that we can calculate it. The third way that we can calculate it is P times the lever arm, which is just lever arm. p times the lever arm. So this is the third way. This is just kind of the same as when we calculate the torque. We said that the torque is the lever arm times the force. And because that we took the derivative of that thing, so the force turns into the momentum. So now let's apply what we have learned about angular momentum into a scenario where a planet goes around a sun. And then you will surprisingly realize that this is the way, or this is one of the ways that you can prove one of Kepler's laws. So everything depends on where we take the axis. So for example, if we have, this is going to be our sun, and make it bigger, and this will be our Earth. So if we take the Earth as the axis of rotation, then it will be the sun that is rotating about the Earth. So it is kind of important to choose where we will take the axis of rotation. So obviously in this scenario we will take the sun as our axis of rotation. Okay, so here is a graph of planet Earth rotating about the sun. And now let's look carefully at it and do the math. So as we know that the angular momentum is shown equal to P times the lever arm, and P is equal to M times V. So M is the mass of the planet, and V is the velocity of it moving around the sun. So let's see if the V is a constant thing or not. So is this planet accelerating? No, it is not. I mean, accelerating in the direction of its movement. No, it's just not, because there is only one force that is attracting that is on the planet, which is the attraction of the sun, that is pointing perpendicular to the motion. So there is no force in the motion of that planet, which means that there is no acceleration. If there is no acceleration, then it means that it shall either be at rest, or it shall either be moving at constant speed. And as we know, a planet is rotating, it's orbiting. So we know that this V is a constant. And then also the lever arm will be the distance from the sun to the planet. And the lever arm, it will also be a constant. So if we times all of them together, then you will find that the angular momentum is a constant. If the angular momentum is a constant, and if you take the derivative of a constant, which we shall get a torque, it will equal to 0, which means that there is no torque. Okay, so this is the first stage of our analysis. Now let's see whether there is a real connection of it to one of Kepler's laws. So let's consider the area that this planet sweeps through. There is one thing that to make clear is that this little arc area over here, we will ignore this, because what we say is that it moves in a very short time at a very short delta theta. So we can consider the movement of these 2 points as a line. So the area that we wanted that it sweeps through will equal to this green part, and then this green part is a triangle. So the area that it's through is the base times the height, which is the distance that it travels through times the lever arm, and times 1/2, of course. And you will find out that if we divide this area by the time, then it will be equal to a constant. So one of Kepler's laws that says equal areas in equal time is actually a word description of the law of conservation of angular momentum when there is no torque produced by the force. The last thing that we will discuss in this lecture will be the conservation of angular momentum. So what happens when there is a large number of particles, and then there are like forces on the particles, there is torque, and then the particle is rotating about something, and yet that object is made up of many pieces, and many forces are acting between them, and also there is an external force acting on that system or that object. So this is a very complicated scenario. So how should we will analyze it? So let's first try to apply what we know. So the torque is, let's say that the torque on the ith particle, let's first talk about that. So the torque on the ith particle is equal to the change in the angular momentum of the ith particle, which is the lever arm times the momentum. So now we know that, so let's like express it mathematically. So tau, which is the torque, it will equal to the total, I mean this is the total torque, and then the total torque, as we've discussed in the second part of this lecture, total torque is equal to all the torque summed up, and it obeys the law of algebra additions. And that will equal to, because we know that the torque is equal to the change in angular momentum. What can we know from, if I write an equal of this over here? Then you will find out that there is a difference between these two expressions. This expression means one of the inner parts, I mean the internal one of a particle, indexed I. But here, this big L, it means the total L, isn't it? So here we are introduced to a new concept, which is the conservation of angular momentum, which is one of the most important concepts that is in physics. And that thing states that the rate of change of the total angular momentum about any axis is equal to the external torque about that axis. So it doesn't have to be a rigid body, it can be anything. So this will equal to external, this will equal to the external torque. So the total torque will equal to the external torque. And why is this correct? Why is the rate of change of the total angular momentum about any axis is equal to the external torque about that axis? If you remember from the first part, when you're talking about the center of mass, we said that all the forces of all the particles that are used to counteract each other, that are used to that are used to attract and repel each other, they are all cancelled out because of Newton's third law, which means action is equal to reaction. And if we sum them all up, internal forces are cancelled out, so what is left behind will be the external force. So this is actually kind of the same analog to this scenario. So let's say that we have a axis over here. Yeah, let's have an axis of rotation in this line, which the axis will be over here. So it will be represented as a dot in this two-dimensional plane. And we have two particles, that is over here and over here, and they are, there is forces acting on it. Let's just only take the perpendicular force. Because of Newton's third law, we know that action equals to reaction, but it is also that the forces, they are in the same line and they are opposite. So these two, they will be cancelled out. So these two talks will be cancelled out. So this is how we got to this thing, this conservation of angular momentum. So the law of conservation of angular momentum states that if there is no external torque acts upon a system of particles, then the angular momentum remains constant. So that is like a deduction of what we have said before. And let's study that concept. So just like how we have studied rotation, we first apply it to rigid body because a rigid body is simplified. We don't need to consider all those complicated factors that can change the shape, the material that when we are rotating it. So various parts of the object, they bear a relationship to another at all times, which is what I said over here. So we know that Li, which is the angular momentum of a particle indexed I, it will equal to the momentum times the lever arm, which is Mi times Vi times the lever arm, and then we will call the lever arm Ri, which is a distance, and that will equal to Mi times R squared I W. I mean omega, this is omega. So how did this change from here? Can you still remember that we said the velocity of something rotating, it equals to the omega times the radial distance. And you know that the radial distance is equal to the lever arm in this scenario, so we can substitute this formula into this Vi. So let's say that there is a new thing called I, and this there is a new thing called I, and I times this omega, it equals to the angular momentum. And now the total, and then you can write I separately. So I will be the total of Mi and Ri squared, because in this expression it means total. So if you want to write this one, we'll write this I independent. If you want to take it out, then it shall also be the total of this thing. So this I is what we call the moment, the inertia of moments. So a body has inertia. So a body has inertia rotating, and a body has inertia when it is moving. So the bigger the inertia it is harder for something to be stopped when once you start to rotate. So this is like an analog to linear motion. If I have a big truck that is like several tons, then because of the mass is very high and all of those stuff, then we know that it has a high inertia. So if once you stop a car with a high inertia, then it will be difficult. And if we put it to the inertia of moment, if we have a high value of this I, then it will also be kind of difficult to start it and also to stop it. So the body has inertia rotating, which, it depends not only on the mass, but it also depends on how far they are away from the axis, which is this Ri. And remember that this is also squared. So the farther you are away from the axis, then the higher the inertia of moment it is. An example, so let's have an example so that we can analyze and have a deeper understanding of this thing. Let's say that we have a stick, and this is a uniform stick. We say that this stick is a rigid body, and this is the center of the stick, and the center is also going to be the axis of rotation. And then there will be a mass, big M, which is hung down over here with a spring. So it is actually like when this mass drops down, this rigid body, this stick, it turns. And then we have two masses of the same mass m and m. Like these are all lowercase m over here. So the first thing is that the masses m are, when they are close to this axis of rotation, then we can see that this m will be falling down at a faster rate. Well, first it is because the m represents how fast this thing is turning. And secondly, if we move these two m's to the end of this rigid stick, then you will find that the big M will be moving down at a lower pace, and it will be like slower, and it will be changing also slower. So this is because the angular momentum is conserved. So we know that the angular momentum is equal to I times omega, and then omega is the velocity of how far the velocity of angles. Yeah, the velocity of angles changed, and this L will be conserved, and because we increased this moment of inertia because we moved the distance of these two m away from the axis, and from the equation of the moment of inertia, we know that it is equal to the mass times r squared. So the inertia is increased, and if this increased, to maintain the same value of this L, then this omega will decrease. And if omega decreases, then this thing will turn at a slower pace, and it will represent as the mass m will be slowing down. Well, someone may ask, what is the difference between between the normal inertia and also the moment of the normal moments and also the moment of inertia, which is also the difference between mass and the moments of inertia. So the biggest difference and the most important difference is that the mass is unchangeable, well, unrelativistically, but the moment of inertia, it can be changed. Because from this equation, we know that inertia is equal to m times r squared. It is not only about the mass, but it is also about how far it is away from the axis. So here I can give you an example. So say that I have a circling plate over here, and it is connected to the ground. There is no friction between the connections of this plate and the ground and everything else. And then I am going to be standing on this rotating plate, and then my system will help me rotate it a little bit. My system will help me start to rotate it. And when I start to rotate it, then there will be an omega produced because I am spinning. If I initially hold my arms like this, but now if I outstretch my arm, then what will happen? So because that angular momentum is conserved. So in the first scenario, this half is working. So in the first scenario, it's L1 is equal to omega 1 times I1. And if I outstretch my arm, that's going to be the second scenario, it will be equal to omega 2 times the moment of inertia 2. Because I outstretch my arm, the mass on my fists, well, we can interpret it as that is moved out from the center of axis, just like how these two blocks of M are moved to the sides of this rigid stick. So the moment of inertia is increased from I1 to I2. And because omega 1 times I1 will equal to omega 2 times I2, That is because of the conservation of momentum, angular momentum. So this angular momentum this omega will decrease. So if I strip my arm, then I will be spinning at a lower pace. And I guess that is the end of this lecture. I hope that you enjoyed, and remember to subscribe and wait for my next chapters.